So, hello and welcome everyone to today's webinar on FirecREST enabling programmatic access of HPC resources. The webinar will be presented by Irini Kutsaniti, and she will be supported by Juan Dorsch. They are both software engineers in the development team of FirecREST. Before starting, just a few words on the webinar format. The total webinar is scheduled for 1 hour. We think to take around 40 minutes for the presentation part. This one will be recorded, and afterwards we will stop the recording and we will go to the question and answer session. That being said, you can already type in your questions also during the presentation in the interface provided by Zoom for Q&A. With that being said, enjoy the webinar, and I hand over to Irini.
Good morning. Hello from me too. My name is Irini, and I will be doing the presentation about FirecREST. This is the second webinar of EuroCC about FirecREST, and if you haven't watched the first one, I would recommend you to do it. The previous webinar looked at FirecREST more from a user point of view, and in this one we will go into a bit more details about the architecture of FirecREST and also some important components and their configuration. Kind of a disclaimer before we start. This webinar was organized with the help of, and it was also funded by the European Commission, and in particular the Castile project. Quickly now, let's see the contents of the presentation today. We will talk about FirecREST, the motivation behind it, and why it was developed at CSCS. We will look at the requirements that an HPC center would need to fulfill in order to install FirecREST and start, so the users of this center could use it. We'll also go into more details about, as I said, about the architecture of FirecREST, as well as some important components of the system. And finally, we will look at the CSCS deployment and the reasoning behind some decisions we made in our deployment. Let's start with the motivation. For a while now, users and developers are all they are interested in developing applications and platforms that can take advantage of the HPC resources. This in the past, it led to different custom solutions that would not benefit neither the developers or the system administrators of the center, since every time we would have an update, we could break in someone's workflow, and in general, it made life more complicated for everyone. So this created a need for the creation of a standard and modern interface to the resources. And this interface would have to deal with different machines and different HPC clusters. It would have to deal with a job scheduler so that the user can submit jobs or manage them. It also would have to give some file system operations, and finally also deal with the different data transfers, internal and external to the center. And finally, FirecREST strives to achieve integration with the existing infrastructure of the center, so that we don't have to reinvent the wheel in every for every functionality, but rather take advantage of the different services that the center provides. So this. In a nutshell, FirecREST is a RESTful Web API infrastructure. That in practice means that a web client or a user can talk to FirecREST through HTTP requests, and the response, in order to do the operations that I mentioned before, work with the workload manager of the system, or move data or do some utilities operation. And then FirecREST, it should reply with a standard format that can be easier to handle programmatically. one very important advantage of FirecREST compared to custom solution is that it enforces integration with the identity access management of the center. Using permanent SSH keys or even passwords to handle this part can be dangerous if not handled correctly. So FirecREST wants to avoid that and just use the IAM of the center. So here, let's see what are the requirements of the system. First and most importantly, the only workload manager that is currently supported is Slurm. FirecREST, besides normal job submission to the scheduler for simulations or calculations of the user, we also rely on a dedicated Slurm queue to handle large data transfers between internal file systems. At CSCS, we have the expert partition, but this would also work for a different dedicated queue for the transfer. And also it relies on object storage service for large external data transfers. When the user wants to upload a dataset for experiment or something like this. This is what I mean external. The object storage of CSCS exposes both the Swift API and the S3 API, so FirecREST is able to use any of those two. And finally, the IAM of the center, the identity and access management, it has to support the OpenID Connect protocol, since FirecREST is using OIDC tokens. Note that the FirecREST is currently still in development, and we are working on making it work with different systems. But for now, we have these limitations. So let's move to some. Let's go now to talk about the architecture of FirecREST. So FirecREST translates HTTP requests that users are making, or a client, into the appropriate operations on the supercomputer. These operations involve different resources, and they are managed by the appropriate microservice. This design makes the development and testing of each component easier, and it provides maintainability, security, and stability, like I mentioned here. Before starting talking about the microservices themselves, some context about the picture. We'll be seeing it in different slides too. All these rectangles that you see are different microservices that can be either completely independent, they can be in their own machine with our own IP, or they can share the same machine and expose different ports. These rectangles that are grouped here are what we call FirecREST, and the ones at the bottom of the page are core services from the center. You can see the object storage that I already mentioned. You can see the IAM of the IAM layer. And also there is a cluster node where FirecREST will be acting on behalf of the users. Every command that has to run on the cluster will be running there. These nodes can be one cluster node, or it can be more. And this little cloud on the top, the web cloud, it's let's say it's some web application, and we will go through an example of what would happen if this web application makes a request to FirecREST to see how that would work. We will go through a simple example. Let's say that we want to list the files inside the directory. So all the requests that are made to FirecREST, they need to include an OIDC token in the header. So the first thing that the client would have to do is acquire a valid token by the OIDC server. And this OIDC server is not really part of FirecREST. It's managed completely separate by the site. And FirecREST will not at any point have the password or long-lasting credentials of the user. It will handle everything with this token that the user will send through the request. So the request will start, the first service it will meet is the gateway. The gateway, it should be the only service from FirecREST that is open to the internet so that the user can access it. And the configuration of the gateway can vary from can be different from site to site, but in general, it's a responsible service that will implement and enforce the authentication and authorization, and it will also have to protect FirecREST or the system by enforcing some traffic control and gathering some information for analytics and the logging of the requests. So the gateway will forward the request to the utilities microservice in this case, because we want to list the files in a directory. The utilities microservice, as I say here, provides file system utilities. This could be list a directory, or uploading some small file, some job script, or removing a file, things that can be done very quickly. In our case, this microservice will check the validity of the parameters passed with the request, and then in order to execute the command in the cluster node, it will need an SSH certificate that it will get it from the delegation microservice. The delegation microservice is a very important microservice at FirecREST. It should be isolated and protected as possible, as much protected as possible, because this is how FirecREST is operating on behalf of the user with these short-lived SSH certificates. We will see more details, a bit more details about it later, but for now, the delegation microservice is a service that will create a certificate for a given combination of username, shell command, and arguments. It will get this. The username will take it from the token, and the rest also from the request. And finally, with SSH certificate, we'll log into the cluster node, execute the command, parse the output, and return to the user a JSON object to the client, which is why it can be much better for code to deal with, because a JSON object should have a standard structure, and FirecREST will take care of of parsing the output and making it easily readable. There are some more microservice that we didn't see in the example. Is the compute microservice, which in general takes care of the request for the workload manager. It will allow users to submit, query, and cancel jobs, basically. We have the storage microservice that is responsible for the data transfer of larger files. It's responsible for the internal and external data transfers. We have the task microservice that keeps track of asynchronous operations, because compute and storage will not immediately reply to the user with what he wants, with the output kind of what he wanted of the operation. They will reply with the task that the user can then poll and see and check the progress. And finally, we have the status microservice that provides information on services and infrastructure in general. So we have some more advanced kind of workflows. Every time that FirecREST interacts with a scheduler, it is creating a task resource. So in a request to submit a job, the client makes the appropriate request to the compute microservice. It will get a response immediately with a newly created task, and then, like I said before, that it will have to poll this task in order to track the status in an asynchronous way. And then we have the external transfers that are handled through the storage microservice. In the external transfers, we are using a staging area. This is the object storage that I mentioned before. And the client will not upload or download the file directly to the machine or through FirecREST. It will upload or download it to this staging area, to an object storage. So the request from the client to FirecREST, it aims to get the URL for this staging area. This allows FirecREST to be responsive and lightweight, since it delegates the large transfers to a service that is more suitable for this. Just a side note here, in order to create these temporary leaks, FirecREST will need to have a service account for object storage, so the users won't have to create users also in the object storage service. FirecREST will be creating a unique URL for every transfer that will automatically expire after a certain time, or could be invalidated earlier with a request of the user. And we have also the internal transfers. I mentioned it before when we saw the utilities microservice. For small files, maybe it makes sense to use the utilities microservice, but there is a maximum allowed file size for these transfers, which is configurable, and you can get it from the status microservice. And there is also a time limit for all commands. So for larger files, you will if you want to move some file from one file system to another, you wouldn't be able to do it through utilities microservice. You will have to do it through the storage microservice, and use this dedicated workload manager queue for internal transfers. FirecREST will create the job script and submit it based on the request arguments to the storage microservice. And now let's move on to some important components of the system. So I mentioned already the gateway. One popular solution to manage the API's gateway, and our solution at CSCS, is the Kong API gateway. It is open source and it is optimized for distributed architecture. It acts as a proxy for the microservice, exposing the public endpoints and routing the request to the relevant services, and also aggregating the response before sending the final response to the user, to the client. The Kong server is built on top of Nginx, and this is a server that will process the requests and execute the configured plugins to give additional functionalities to the gateway. The configuration of Kong can be pretty straightforward, although you can do something different in your site. First, we need to redirect its request should be redirected to the right microservice, and these microservices can be in different paths in the same machine, or with different ports or different IPs. The Kong configuration will be checking the JWT tokens, the OIDC tokens that I mentioned. So it will need to hold the public key of the OIDC server in order to verify them. And finally, we are using some plugins for our deployment. We use the JWT plugin, which is set to be global, so that all requests are verified. And we verify there the validity of the token, which is passed via the header of the request. We check the key of the authorization server. We make sure that the token is not expired, and if it is expired, we will discard this request and give a code 401 or something similar. And then we have the request termination plugin, which is just to reject wrong queries. And then a very important plugin is the rate limiting plugin. This is especially useful in a production environment, since it can limit the number of requests that can be made in a given period, and it ensures that the server is not going to be overwhelmed and possibly debilitated even. This is important to protect the microservices from malicious attacks, but it is important protect from buggy code that could be stuck in an infinite loop by mistake and overwhelm the system with a lot of requests. And finally, we have the Zipkin plugin, which Zipkin is a tracer, but we don't use it directly. We use Jagger, as we'll see a bit later. Jagger is it's somewhat compatible with Zipkin, so that it and this was the available plugin, so we can receive traces. Jagger can receive traces that were generated for Zipkin. That's why we use this plugin. Let's move on now to the delegation microservice. You might see it later, certificator. This is why I write it like this here. We already mentioned it. And as I said, this microservice is very important. It should be kept isolated and as isolated as it is possible and protected. And it's basically a certificate authority that can issue SSH certificates for the users of the system. The full configuration. Well, the other things I think I already have mentioned, but let's see a bit about the configuration of this microservice. The full configuration of the microservice is a bit out of scope for this presentation, so we'll go through the high-level kind of idea. The system administrators of the system have to create a pair of certificate authority keys, and the delegation microservice will need this private key in order to create the SSH certificates for the cluster nodes. I write here the machine, but I mean the cluster node. And the cluster node will need the public key to validate these certificates. To validate that the certificates were created indeed by this microservice, basically. The certificates that are created for a dummy key that is used by the microservices, and in this way only the microservices are able to use these certificates. And so even if somebody could get the certificate, they wouldn't be able to use it without this dummy key. And here even after the microservice will have the certificate, like we saw in the utilities, there is some extra checking that we do on the cluster node. The command that we want to use is not going to immediately run the command, but it will run a filter and logger. It will run it through a filter and login wrapper script. In this script, we will validate the certificate type and the certificate signature. We will check that this command is one of the allowed ones. This is another thing, that FirecREST will not execute any command on the system. We have a list of allowed commands that are the only ones that are allowed to be executed. And if everything is okay, then it will execute the command. An important part here is that it logs every step of the way. It logs every check that it makes this wrapper script. We already saw a bit about the IAM layer, but let's give you some more information. At CSCS, we use Keycloak to get these OIDC tokens, and the way that FirecREST integrates with the IAM is by verifying the signature of the token using the Keycloak's public key. The other thing that we check for is that the token will have a custom scope to make sure that this client is registered, was registered specifically as a FirecREST client and not any kind of keycloak client on the machine. And some more information about what are the supported OIDC workflows. The ones that we at least have tested with FirecREST. We have the authorization code flow, which is the type that is used typically for a regular web application executing on a server. In this grant type, the client will exchange then an authorization code for the access token. And this is considered the safest choice since the access token is passed directly to the web server hosting the client without going through the user's web browser or risking exposure. Then there is the PKCI, the proof key for code exchange authorization code flow, which is called also PKCI. And this was originally designed to protect the authorization code flow in mobile apps, but it can be useful for every type of client, really. In this code flow, it introduces a secret created by the application that can be verified by the authorization server, and this secret is called the code verifier. And additionally, after that, the application creates a transform value of the code verifier called the code challenge, and sends this value over HTTPS to retrieve an authorization code. The thing with this code flow is that it can be more safe in the sense of that even if a malicious attacker can intercept the authorization code, they cannot exchange it for a token without the code verifier. And finally, then there is the client credentials flow, which is very convenient for testing and can be very useful for creating automatic workflows in the form of scripts. But this is typically used when you have an application that is asking for an access token for its own resources. Is not supposed to be handling different users. This application is kind of connected to this one user. A different component that can be used with FirecREST is OPA. OPA is an agent that can be used to authorize fine-grained access to specific resources in the API. For now, the way we use OPA with FirecREST is to limit access to the TDS environment. The TDS is the test and development environment. When the code when we have the FirecREST that is on production, and there are no restrictions on who can use it. But for the TDS environments, we want only the developers or the system administrators to be able to use it and test the functionalities. And finally, another useful component of the system is Jagger. The reason Jagger is useful for FirecREST is because one request can trigger actions in many microservices. And then it becomes very complicated to track the problems. If a user has done, you will see afterwards an example, but maybe the user has done a request into the storage microservice and he's getting an error, but the error might be coming from some secondary request in the task microservice or somewhere else. So we use Jagger, which is an open source tracing system for distributed microservice, and it was originally developed by Uber. The gateway needs to add an identifier to its new request, and then microservices will have to propagate this identifier in every subsequent request. And we also log this identifier with every command in the cluster node. here maybe will make it more obvious why Zager is useful. Here you see the traces from, originally all this came from one call to the storage microservice. Somebody wanted to use the internal RM endpoint, and if you remember, in this case for internal RM, we will have to create a job that will run on this dedicated Slurm queue. So you have here the original request from the user that is still in Kong, which forwards the request to storage. This calls to certificator is what I was calling before the delegation service. This is because before submitting the job, the FirecREST will make some checks, and then it will, if the checks pass, then it will forward it to the compute microservice. And in Zager, you can also see how long this request lasted and in which function it has spent its time. For example, now it's in the submit job upload, which will also have some calls to the certificator. If you remember also, when we submit jobs, we create a task, which is a FirecREST kind of different identifier. So the FirecREST will reply to the user with a task here, and you see this is why the Kong how can I say it? The Kong will reply to the user, and there will be some asynchronous. There will be more tasks. There will be more actions that will be triggered from the certificator on the task microservice. And finally, at the end, when the job has finished and everything's okay, or when the job is at least successfully submitted, then the task will be updated and the workflow will have finished. But this allows us to, the nice thing with Zager is it allows us also to not just see the length, how much time it has spent in each microservice, but we can see what kind of requests were made. For example, here storage, this is for a post request. We can see the status code, the URL that it was using. So if a user is having a problem, if they open a ticket, then it's much easier for us to, if we have this identifier, it's much easier to track the whole life kind of this request and see where the problem actually was. The thing you don't see here is the logs from the cluster node. These are not here, but these logs are sent to Elastic. The machines that are running the microservices, they have file bits, so they send the logs to Elastic. So we log also the command with the identifier, for which request this command was performed, and then we can see also possible errors there. I didn't put a slide here, but it's important to kind of say that if you open FirecREST to many users, it's very important to have an easy way to access the logs and maybe search them. This is why we're using Kibana in our case to track the different requests. And finally, these are some points about the deployment at CSCS. As I mentioned already many times, only Kong is open to the users, and Kong can, well, I say can, but Kong has rate limiters so that we can protect the system. An important decision at CCS and that we made is to not have the user's file system mounted. This decision was made for security reasons, and it's not necessary for your site. It can be different. It can be configurable. And the reason we did that is because, let's say we have a malicious and evil application that it holds the OIDC token of a user for legitimate reasons. Let's say the user asks this application to make some requests for him, but the token itself, it would last only for a short period of time, and the application could not take advantage of it indefinitely. On the other hand, if the home of the user is available to the app, then on the background, the application could inject some SSH keys in the user's home directory and can have complete access to the user's account indefinitely until somebody notices it or realizes it. For this reason, even the jobs that are submitted through FirecREST, they don't have access to the user's file system. Different things that we do at CSCS is that all the microservices talk amongst themselves with HTTPS requests, and also we have some additional network rules so that not every microservice is available for all the other microservices. Of course, they're never open to the users, but they are also not open to all the rest, to all the other microservices. They're open only to the necessary ones. And this I already mentioned it, but we also use OPA. That the way we use it is to deny access to normal users in the TDS environment. So finally, let me give you some more links to find more information about FirecREST. The first link is the complete API, where you can find all the endpoints and what are the responses that you should be expecting. FirecREST is an open source project, and the source is on GitHub on this link. The GitHub repo, it includes a template client in Python and a demo environment in Docker. So you don't actually need a real cluster to test FirecREST. You can use this demo environment and develop your own clients before getting access to the real cluster, to the real HPC center. We have the read the docs page for some documentation, and also there are some examples of if you want to use the HTTP requests. And we also have a Python library for the API. In case you're developing something in Python, you can be using it with this with the FirecREST library. And finally, I have put here the link for the EuroCC page. We have also a mailing list that is, I think, firecrest.cscs.ch. You will find this mailing list at the EuroCC page. And more information, you can also find the previous presentation. That is also. It has more information from the user perspective. And that's it from me. Thank you very much for your attention.